and Sujay reminded me that in the 5 years of IFML, strangely, I had never given a single seminar or an MLL seminar or anything. I always wanted all of, I don't like being in the spotlight, so I always wanted, to show off all the great things that you guys are doing. So we've had many seminars with you speaking and with external speakers, but Sanjay twisted my arm and said, maybe for the very last one, you should give it since you've never given the seminar. So here I am. I've given this talk at the Simons Institute, although I've updated it. And I know that maybe a couple of you have seen the talk. Certainly Kostas and Arsen have seen this talk and know everything about it. And those guys have done really amazing work in this area. And it's been a privilege to work with them. And some of my other students I'll also mention have been key contributors. And so I'll mention their work too. But yeah, I did want to highlight them. So I want to start by talking about generalization. And many of you, I assume, are familiar with the classical notion of pack learning or epsilon delta learning, where a learning algorithm gets to see some training samples from some fixed distribution, IID samples, and then is supposed to output a classifier H that has error with respect, small error with respect to a new draw from this distribution. And for most of the talk today, we're going to be talking about classification, so just 0-1 loss. But what I want you to think about is in this classical epsilon delta model that was invented by Vapnik, really, who should get just as much credit as Valiant for the pack model. Most people are familiar with this model. I'm happy to go over it if you're not familiar with it. But the point is that typically in this model, the distribution, there's only one distribution, D. So you're training on this distribution, and then you're asked to perform well with respect to a new draw from this distribution. So that's the test distribution too. And what I want to argue is that this term, we call this generalization, when you can perform well with respect to a new draw from this distribution. Maybe we shouldn't call that generalization. Maybe we should call it imitation or mimicry. Because we're assuming that the training distribution is the same as the test distribution. And I think in this world, this D train equals D test world, or the pack world, there's been an enormous amount of progress, both theoretically and experimentally. And if I wanted to say even more controversial things, I could say at a super high level, maybe we should even consider this sort of a solved problem. If I want to build a model to learn a distribution of images, I can train a diffusion model, assuming I have enough images to train on. And they do very well. I mean, as you all know, you can learn distributions of very complex images. I mean, Sanjay just gave a talk on that. If you want to learn the distribution of sort of English language, you can train a large language model to do that, and it performs very well. On the other hand, in this world where that I think is much more important, where the test distribution is not the same as the training distribution, relative to when D train equals D test, very little is known. And so Sujay mentioned that I am working on protein engineering, and so sort of one I want to tell you an anecdote about a meeting that Danny and I have had, Danny Diaz, who's not here, but my research scientist, on protein engineering. So a protein is just a sequence of amino acids. There are 20 amino acids. K happens to mean lysine, L is leucine, I is isoleucine, V is valine, and so on and so forth. So a protein is really encoded by a sequence of one of 20 amino acids all in a row. And one of the major goals of protein engineering is to take one of these sequences as an input and predict what happens to this protein's function for a particular function if you make a mutation on this sequence. If I mutate the V to some other amino acid, how does it affect the function of the protein? And so people have built many, many classifiers to try and predict, what happens when you, make these mutations. And the most common approach is to do sort of a BERT type pre-training. So you take hundreds of millions of amino acid sequences, and for each one you mask out 15% of the amino acids in that sequence, and you train a model to predict what amino acid was masked out. Okay, so it's just like you would train a language model. You can train a language model on these proteins, and people build models by doing this exact type of training. Okay, and what's really interesting is that people measure, how well do you reconstruct a protein sequence? You take a test protein sequence, mask out 15% of it. How well does your model predict what was there? And people measure the accuracy of that, and they call it something called wild type accuracy. Like how good is your model at predicting what amino acids have been masked out for a sequence that was found in nature? The problem is that if you build a model, and we've had many conversations with biologists, you build one of these models, and there are many papers that report wild type accuracy for their models. And then you ask them, like, well, what would happen if your model was 100% accurate? That would be great, right? And they're like, yeah, that would be great. And then we say to them, actually, it wouldn't be great, because then it would just predict proteins that we already know about in nature. And the goal of protein engineering is to come up with new proteins that you haven't seen in nature before. So like 100% wild type accuracy it results in a model that's useless. And they go, oh yeah, you're right. We don't want 100% wild type accuracy with our models. Then you say, okay, well, would you like 80% wild type accuracy, or 65% wild type accuracy, or 90% wild type accuracy? And then they start to realize, oh yeah, this is the totally wrong metric.
Accuracy of predicting what?
Oh, so no, just the sequence. So you take a sequence, you mask out 15% of the letters, and then you ask your model to predict what letters were masked out.
Got it.
That's it. Yeah. Just like you would, mask out words in a sentence. And so, they were building these models to try and improve wild type accuracy, but once you get to 100%, it's like you're predicting everything that already exists. We're not interested in that. So that was kind of weird. And if you talk to biologists, what they mean when they say, like, does your model generalize? It turns out that they always mean, does it work out of distribution?
Wait, I mean, 100% accuracy on proteins that already exist simply wouldn't determine what happened. Like if that 85% had never been seen in nature, the data set, right? It would just leave that undetermined.
I didn't totally understand your question. I mean, like, if you give me if you draw a new protein from the protein data bank, so you have a validation set.
Yeah.
Or you know,
but let's say we're trying to engineer a new protein.
We're trying to engineer.
Been seen in nature.
No. So when you engineer a protein, it's always a protein that already exists in nature. And the goal of engineering is to like tweak it. So to make it better.
All right, thank you.
Then you're just going to get back to nature.
I got it.
Yeah. So for biologists, like, generalization always means out of distribution. Can you come up with things that are out of distribution? Yeah. So there, for example, another example is you train a model on enzymes or something, which is a type of protein. And then you want to predict, how mutations are going to affect something on antibodies, which is a different type of protein. It does very poorly. In fact, we know that like AlphaFold does very, very poorly on predicting structures of antibodies. So there's a huge distribution shift there. So they're always interested in out of distribution.
I have a question.
Yeah.
I guess like just trying to understand this, in my world, it would be a good thing if it got 100% if it also had like a conditional input that depends on something I care about, right? So then like maybe I want the unconditional to be 100%, but then if I can condition it on something I care about, that would be a good model, right?
Condition. I mean, even for a structural, I mean, for us, like, well, I don't know why it's good for you. It's not good. It's not good in this
like
particular
if I have
thing.
X, I want it to have, I want it to produce a new X in the distribution, but if I can now condition that model on Y, I want it to produce something new, right? But it's only because it's conditioned on Y, which is like somehow different than the distribution D.
Yeah.
Is that not?
But in some sense, that is a distribution shift because when you condition the measure as change. For fixed Y, it's a new distribution. You can just look at Q of dot equal to P of dot given Y. So it is essentially a distribution shift.
Yeah.
And so in that sense, it is out of distribution.
Well, I guess I'm just arguing that then maybe wild type accuracy would be a good metric for the original distribution.
Yeah, I mean, I guess what we found is that, when you move to different so what you can do is you can come up with different metrics, which is what we've done. And like, you can then measure. So, I mean, I don't want to get too involved in this, but like basically you can show, you know, there are these, all these you can do this type of pre-training, and then you can look at downstream applications.
Right.
And, you know, you can see that as your wild type accuracy increases, the error of the downstream application starts to decrease. Whereas, you know, you'd really like a metric that's a proxy for that, which is what we did in a different paper.
Yeah.
Okay. Maybe like a simpler and more compelling example is, you know, AI for health. So, you know, you'd like to come up with a model that can detect cancer from MRI. You build a foundation model using known images, maybe from some population of patients from some distribution. And then you'd like to deploy it on a new distribution of patients. So that's like an unlabeled test set. And I think everybody is really concerned that, you know, and there are known, like, you know, documented instances of this where the foundation model that you built on one population of patients just fails miserably on a new population of patients. And so, you know, you're really worried, like, I mean, we all know that we're overfitting, but you're really worried that, you know, you're going to deploy it on some new population of patients that is different from what you've trained on, and it's going to perform very well. And I think this is one of the major reasons why we aren't seeing more of a deployment of AI tools to predict things in healthcare, because we really are worried about these types of distribution shifts. Okay, so that said, now, you know, tried to make the argument that I think, you know, learning with respect to distribution shift is maybe like, you know, the most important problem in machine learning. I want to tell you for most of this talk, I don't know how much time I have left. For most of the talk, I want to tell you about this model of learning called TDS learning, which is testable learning with distribution shift. And it's a model of domain adaptation. So we're going to try and capture this idea that your training set is different from your test set, with the goal of still coming up with efficient algorithms. Okay, so yeah, so before I do this, how many people are familiar with domain adaptation? Raise your hand if you're like familiar with the formal models of domain adaptation. Okay, like not that many people. Good. Yeah. So it's kind of surprising. I mean, it's a very nice model, but not nearly as many people have heard of it. So let me tell you about the model. So in domain adaptation, you have D, which is a distribution. It's your training distribution, and you, the learner, always get to see labeled samples from D. Okay, just as before. And then there is D prime, which is a test distribution. Again, on your domain cross -1, but in this case, the learner only gets to see like unlabeled samples from this distribution. So you take draws from D prime, and then you imagine like deleting the labels, and you present that to the learner. Okay. Now the goal of the learner is still to output a classifier H, so that the error with respect to new labeled samples drawn from D prime is actually small, is at most epsilon. So again, think about the AI for health setting. In D, I'm going to have a population of patients, and I know whether or not they have cancer. I'm going to train my model on D, and then I would like to perform well on D prime, which is going to be an unlabeled set of points, and that's going to correspond to patients who I actually want to predict, like whether or not they're going to get cancer. So I don't have their labels yet. Okay, and what we'd really like, what would be awesome, is if we could always output a classifier H, you know, that does well with respect to D prime. Okay, that would be great. Does the setup make sense? Feel free to, you know, interrupt me here. Yes.
Do you assume y given x and d prime is the same thing as in d?
Oh, I'll talk about that in a second. We'll get to that. There are two cases. Yeah. Good question. All right. And so to address your question, so now I'm going to tell you about this parameter lambda. Okay. And lambda is like, it's the error of the best fitting classifier with respect to both D and D prime. Okay, so you take the min over all functions in some concept class C, you know, you can think of C as like half spaces. That's what we're going to take it to be in just a second. It's the minimum over all functions in C of the error of that function on D plus the 0, 1 loss, the error of that function on D prime. If this confuses you, you can assume that lambda is 0, which means that there actually is a ground truth function labeling everything in D correctly and everything in D prime correctly. But of course, like, you know, you might only see some part of the distribution when you take draws from D, and you might see a different part of the distribution when you take draws from D prime, and therein lies the difficulty of solving this problem. Okay, makes sense so far? Good. And again, okay, so our goal, just like in pack learning, you were trying to output a classifier that has error at most epsilon. Here, I am going to let you pay with respect to lambda. So the error, you want to output a classifier H such that the error of H with respect to D prime is at most some constant times lambda. I'll let you, be within a constant factor of lambda plus some error, plus some small epsilon. Okay, any make sense, right? Sort of makes sense what we're doing. And it turns out you have to pay in lambda. Like lambda is unavoidable. You can prove that. Yeah.
Lambda is defined as the both on D and D prime.
Yes.
But then the left-hand side is only on D.
Right. No, left-hand side's only on D prime.
Yeah.
All I care about is error on D prime. That's my test distribution. And the whole, all I care about is the test distribution.
So that you have to pay at least the minimum error on D prime is obvious.
Yes.
That you have to pay also at least the minimum error on D.
It's
what's
not
the
obvious.
argument to that?
Okay, so it could be the case that Costas will correct me here. So it could be the case that D and D prime have just labels that are flipped for the same points.
Good.
Something like that, right? Yeah, we carefully have the examples all done in the paper, but yeah. Okay, now I have the pleasure of telling you basically every result that's known in domain adaptation in one slide. So domain adaptation has been around for like 20, 25 years, and every single result is a generalization bound. No efficient algorithms. And all of the results are of the following form. Take an H, fix a classifier H. The error on D prime, which is all we care about. We only care about the error in the test set because I only care about classifying new patients, telling them whether or not they have cancer. The error on the D prime is at most the error on D, which makes sense, just as you would expect, plus lambda. As I said, it's unavoidable. You have to pay lambda. Plus, now here's the kicker, some notion of distance between D and D prime. And that makes sense. Like if D and D prime have nothing to do with one another, then they should be far apart. You're going to have to pay that with respect to the error of H. Okay, and so they're generalization bounds. As you change different notions of distance, you will get slightly different generalization bounds, and there are many papers written about this. Yeah.
And this you can get even without unlabeled samples from D prime.
Yes.
Yeah. So
No. Sorry. Can you get this without? Yes. Exactly. Yeah, you wouldn't need anything about D prime. Correct. Yeah.
I mean, for distance, should I think of something like variation distance?
Well, let me tell you. Here's a common notion of distance, and it's actually this is like maybe the most common distance. It's something called discrepancy distance, which is interesting if you're into pseudorandomness because it is a notion of pseudorandomness, and that's what was interesting to us. But let me just tell you what this is very briefly. So it's the supremum now over all pairs of functions, f and f prime, of the probability they disagree with respect to D minus the probability they disagree with respect to D prime. Okay, so it's how much they it's a notion of discrepancy, like how much they differ with respect to D versus D prime. And if this quantity is small, it truly does mean, I mean, you can prove, I mean, it's not difficult to see that it means that D prime is pseudo-random for the function class C with respect to the base distribution D. Okay, so this is like the most common measure that people look at. And it's in these papers of Ben David et al. And Mansour et al.
This is only on the distribution of X.
Only on the distribution of X. Yep. Yeah. Good. Yeah.
So if you had like another notion of distance like L1 or Wasserstein, does that give us more discrepancy distance? How are they related?
How are they related?
Yeah, but you cannot, like the point of these is that if you have bounded PC dimension, you can actually use a small number of sums to test it. But TV distance you cannot.
Yeah. You could use TV distance or something, but I don't know how Wasserstein is. I don't know if it implies discrepancy distance. Is that true?
Sorry?
Small Wasserstein implies small discrepancy distance. I don't.
I'm not sure, but
I'm not sure exactly what that implies. I know where to look it up though. So here's the big point I want to make. These bounds are useless. Okay, totally, in my opinion, like totally useless bounds. Why are they totally useless bounds? Because this quantity, distribution, discrepancy distance between D and D prime, you cannot estimate in any way efficiently. It involves an enumeration over all pairs of functions from your concept class. Okay, so imagine like you look at one of these papers, you see these bounds, Like, sweet, I'm going to apply this generalization bound to my classifier. You know, you get your classifier on your training set, and you go and you plug in this bound, and you're like, oh, wait a minute, I have no idea what the error of H on D prime is going to be, because I just can't compute distance of D and D prime.
Isn't the problem much worse than that you can't estimate it? I mean, isn't the problem that the truth is that in practice it is typically too large?
No, I don't think it's necessarily too large in practice. I mean, I think the hope is, for example, if you're building a classifier for cancer, that actually the distance isn't too large.
Okay, I mean, I was thinking that, we would like our ML models to generalize even to distributions that are easy to distinguish from our training distribution.
Well, I actually don't think that.
Easy to distinguish could be as simple as, like, I flip the value of 1 pixel. Right now, in principle, it's totally distinguishable, even though I haven't really changed anything too important.
I mean, I think the goal of these models is just somehow detect, like, oh, my classifier, like the real question here is, I want to detect, is my classifier that I've trained on D, like, is it going to bomb on D prime or not?
So you have it's a more limited goal in a way, right? Like you're fine to just say, look, this distribution is too different, I give up.
Well, these bounds force you to give up. Yes, but you're heading towards the model that I'm going to define in a second. Yeah. But I don't feel like that's I think that's actually a very ambitious goal. It would be amazing if what we don't have right now is the ability to take a foundation model and say, like, how's it going to perform on this test distribution? We have no clue. And to me, that's like, so not a limited goal. Yeah.
Your message is not that these bounds are useless or loose. Your message is like they're not tractable. That's what you're saying.
Useless in the sense that, like, they tell me nothing. If they tell an efficient algorithm nothing.
Are they loose?
I don't, but I mean, in some sense, but no, but they're still useless in the same way that Rademacher complexity bounds are useless. I can't estimate the Rademacher complexity of, so, like,
They're not loose bounds.
yeah, but loose and useful are different notions.
So
Yeah.
that's your message.
Like if I give you an exponential time algorithm to sort a bunch of numbers, I'd say that's a useless algorithm.
You're saying it's not computable.
Yeah, that's the difference between computable versus.
Yeah, useless if it not efficiently computable.
But there's a common algorithm in domain adaptation is trying to finding a projection, you minimize the distance in the projected space between the original domain and the test domain.
Actually, common things that are done look at like density ratios between, they'll like what can I bound like the density ratio between like my test distribution and my training distribution, and those are also intractable to compute. I'm not saying that, and actually even like there are some heuristics, but even the number, there are very, very few heuristics even for doing this. Like I know what they are. They look at checkpoints and stuff, but again, very little known. Yeah.
Is this computational lower bound like provable, maybe assumptions on pseudorandomness?
You can prove, we have a paper where you can prove that the discrepancy distance is NP hard to approximate or test. So yeah. It was surprising that wasn't. And I guess an even broader point that I would like to make is about like something else that like we've been trying to tackle in this line of research is that something about assumptions. And I think things that we take for granted in our, at least TCS people take for granted in their field, and that is that in learning, which like in TCS is great because we do primarily we do worst case analysis of algorithms. And when you do a worst case analysis of an algorithm, implicitly you're getting a proof that your algorithm worked, like a guarantee. You know that merge sort is going to work on every sequence you give it because you prove that it worked on every sequence. But when you run a learning algorithm, it's inherently an average case problem because you're receiving examples from a distribution. And so proving that it works or getting a proof that your algorithm works is somehow much more subtle. And typically people have to make assumptions to prove that your algorithm works. So like if you do compressed sensing, your design matrix has to satisfy RE. Otherwise, like, your algorithm isn't going to work, but you can't test if your design matrix satisfies RE. It's NP hard. If you want to learn neural networks, give provably efficient algorithms for neural networks, typically the marginal distribution has to be Gaussian, but you can't test if the marginal distribution is Gaussian efficiently. So you just have to assume that it's Gaussian, or, like it's the problem with average case analysis. How do you, if I have an algorithm that works only on the average case, then I need to somehow assume that the assumption is true in the average case model, because typically I can't verify that that assumption is true. And then you end up in this weird space where it's like, well, I don't know if my algorithm worked or not, because I can't verify the assumption underlying the algorithm, which is a strange, to me, truly does undercut, like, we like to talk about the importance of provably efficient results or provably efficient algorithms. I'm a big believer in them. But if it relies on an assumption that I can't verify, then to me, it sort of undercuts some of like the point of what you're trying to do. Okay. Yeah, and as I mentioned, like this also pops up when people look at Rademacher complexity, which is one of the fundamental quantities in statistical learning theory. You can't estimate it efficiently. So like all these Rademacher complexity bounds, like, are they useful? I would say no. So Arsène, I think, I don't know exactly what he was motivated by, he can tell you, but I think trying to get at some of these, where's Arsène? Okay. Trying to get at some of these issues, I think motivated him and Renit to define this model of testable learning, where you are able to kind of verify some of the assumptions underlying the learning algorithm that you have. And what we showed in a follow-up paper is that it turns out that Rademacher complexity actually tightly characterizes the sample complexity of testable learning, where you can actually verify some of these assumptions. That's sort of an aside. Let's get back to domain adaptation in the interest of time, so I can prove some interesting things to you. Just a reminder of what the model is. So this is what we were. Oh yeah, finally, I can define for you the model that I've wanted to talk about since the beginning of the talk. So now here we are, TDS learning. What is TDS learning? So in TDS learning, you're going to get samples from D, and now you are going to need samples from D prime. And you're going to run, the learner is first going to run a test on samples drawn from D and D prime. And if the test accepts, it will output a classifier H whose error on D prime truly is like within epsilon of optimal. It's like order lambda plus epsilon. And when the test accepts, you will get a proof as if you had run merge sort. Like you will get a proof that your classifier does well on D prime. Now the test may reject. Okay, that's the caveat. That's how we're sidestepping a lot of things. Like your test might just reject, in which case, all bets are off. You don't learn anything. And so why isn't this, so this model is this okay, or is this a vacuous model?
I mean, so far
it's vacuous because your test could always reject, right? Okay, so that's why, so the key thing here is, I should do this, is that with high probability, if the marginal like dx equals the marginal d prime, then your test accepts. Okay, so if you're back in that scenario, so your test can't always reject. If you're back in the scenario where the marginal distribution of your training set actually equals the marginal distribution of your test set, then your test is forced to accept. So it's really doing something non-trivial. This is similar to what happens in testable learning. Yeah.
For running the test, do you need labels from D prime as well? Or
no. No, this is what makes everything so hard. You don't have labels from D prime. And so I'll show you some tests that we run. Yeah.
So, but if dx prime then shifts from dx, then you have no guarantees.
Great.
This is sort of the domain adaptation case.
Correct. So two points I'll make. First of all, as we'll see later in the talk, I'm going to relax this. Okay. So don't worry about that. We'll relax this. But number two, the great thing about the sound, so this is soundness. Whenever your test accepts, like even if D and D prime are different, whenever your test accepts, you get an ironclad guarantee that your classifier is good on D prime.
But it may never.
It may never, but when it does, you get an awesome guarantee, and that's very powerful. Okay, so let me try and convince you over the rest. I actually think even if just this is already like if you can satisfy this, it's a very, very powerful guarantee. And maybe you'll see why as we move through the rest of the talk. But anyway, we have follow-up works that relax all of these things. Okay. Okay, so let's just get familiar with the model. Yes. If it has to be a computationally efficient test, yeah. Otherwise, like, what's the point? Right. Agreed. Okay, let's just get familiar with the model. So,
I mean, isn't there anything interesting to say just about sample complexity here?
Oh, there is
Okay.
definitely. So an upper bound in this model turns out to be the Rademacher complexity of the function class with respect to D, the base distribution. Only D.
Does your test require to know the classifier?
Nope.
So
I'm going to show you some tests in just a second.
How's Rademacher complexity different from VC dimension?
It's distribution specific.
Okay.
VC dimension is
Fine.
super worst case. It's always the wrong measure. Okay, so why is this is a questions for the audience to see if you're following along. So question 1, why is TDS learning more general than PAC learning? Like truly mathematically more general than PAC learning.
Because D prime could be different.
Okay, yes, but more to the point, in PAC learning, D always equals D prime, and you always have to output a classifier that does well. In this model, when D does not equal D prime, then you may reject, but when they are equal, you have to, so an algorithm for TDS learning will imply a PAC learning algorithm. Okay, and so kind of the dream scenario for one line of research is in some sense, one line of research is take all of your ordinary learning results, like in the PAC scenario where D train equals D test, and see if you can somehow figure out how to port them into this model and come up with algorithms that work all like in this much stronger model. Okay, and that's one line of research that we've been pursuing. Here's something maybe a little more interesting. So remember in PAC learning, there's the delta parameter. That's like your confidence parameter, like the probability that you output a classifier. So in PAC learning, let's see who remembers, like how do you amplify, like say you have a PAC learner that works with probability 1%. How do you amplify it to get a PAC learner that works with probability 99%? Who remembers how to do that? Boosting is with the epsilon parameter. This is the easier, this is much easier. This is a delta parameter. Multiple runs. Yes, exactly. So what you do, if it only works with 1%, right? You run it, and then I just take more samples from D, and I see like, is its accuracy epsilon or not? If it's not, I'll rerun it, keep doing that. Okay, notice, interestingly, in TDS learning, you cannot do that. Because imagine I have a TDS learner that works with probability 51%, and I run it. How do I know if it has low error or not? I don't see any labels from D prime. So I guess my point is already like even these simple things like amplifying the error probability with the delta parameter become non-trivial in TDS learning. You can do it. It turns out the way that you do it is you take the majority, you run it several times and you have to take the majority of all the classifiers. And it's not like super deep or anything, but you have to do various averaging arguments to show that it works, but you can do some amplification here. Okay, here's another puzzle that I like for TDS learning to give you a feel for like why TDS learning is sort of difficult, okay? So consider the following toy scenario of TDS learning. So again, the C is going to be half spaces. Lambda is 0, okay? And your ground truth function, like I'll just call it f star, like let's assume it's sine of w dot x plus theta, where w is a unit vector, theta is some value in the reals. And I'll also tell you like d of x, the marginal distribution on your training distribution is a spherical Gaussian. Okay, it's like the simplest possible scenario. You're trying to learn a half space. It classifies everything correctly. Lambda 0, the training distribution is a spherical Gaussian. Okay, now imagine that you take your training samples. Imagine that all of them are positive. Every single training sample you see is positive, which could happen. Okay, now like in PAC learning, you would immediately just accept. You would immediately just say, okay, we'll just output all positive. That's my classifier. Okay, but here, the problem is, like, yes, when you get examples from the spherical Gaussian, you see positive examples, but what if D prime is somehow putting weight on part of a distribution where there are some negative samples? Like, what should you do? I mean, how do you, I guess my point here is, let me know if I'm not being clear, that this seems like a very difficult situation to be in. Like, it seems like you've learned nothing. You took all your samples from the training distribution, they were all labeled positive. Like now you have these new samples from D prime where I have no, like, what can I do? Like I'm stuck, right? Yeah.
So just to parse this, I mean, you're saying that the dx is just an isotropic Gaussian?
Yeah, spherical Gaussian, yeah.
And in the accept scenario, dx prime would also be that same distribution.
Well, that would be one, yeah, we would be forced to accept in that scenario, yes.
Yeah, so, I mean, if you get very unlucky and all of your x's land on one side of this half space.
Oh, well, there's a high probability that takes care
I'm
of that.
asking, like, what is that precise, like, parameter that you're allowed to say I reject, even though in fact dx would equal dx prime? Because
Oh,
here
no,
you see
I mean,
those
it's
numbers.
extremely small.
So this would be like.
That's not the issue here. The issue is like, you don't know, you only see positive examples in your training set.
Yeah.
And now I see these unlabeled samples from D prime. And I don't know, should I reject or should I like accept? Like, I can't test. I guess one important thing maybe you're bringing up is like, I can't test whether D prime is a spherical Gaussian. Like there's no like all the algorithm that turns out to be like require exponentially many samples in your dimension. You can't, you think like it's not even super well defined. Like I give you a bunch of samples. I say, did this come from a spherical Gaussian? You're like, well, maybe it came from a discrete distribution and with this support.
Yeah.
So there's no simple way to kind of determine like, is D prime a spherical Gaussian or not? So you can't just try and test that. You have to do something else. Yeah.
So somehow, even with unlabeled examples, though, you can measure the distance and you could reject on the basis of that, right? D prime looks very different from D. So here, this case would only arise if D prime is just really a different.
Yes. So you could, so there are some simple cases like that that would allow you to reject, but in general, something like that will not work, just computing distances. I guess my question for you is, what I want to see, what I want you to tell me is like, I'm tricking you a little bit. Like we actually have learned something. What have we learned about F star if we only see positive examples? Yeah.
I mean, I don't know that much about half spaces, but we should know some large region is like in the half space that is in the set, right? Like if you only see ones, that will imply a bunch of other things will also be ones, right?
You're on the right track. Something simpler. You only see, remember, W is a unit vector, X is a spherical Gaussian, and we only see +1. So what does that mean we know about F star?
I don't have the answer, but I have a question. Your D is not the spherical Gaussian. It is a slice of spherical Gaussian.
No, the marginal distribution on the covariates for D is a spherical Gaussian.
Right, but then if I only see the positive examples, you have thrown that away. So that's not an IID sampling from D.
It is an IID sampling. Okay. It's because theta, it means theta is really large.
Okay.
Right? Right? Like because W dot X is also distributed according to according to just a univariate Gaussian. W is a unit vector, X is spherical Gaussian, W dot X is just N01. So the only way that I see all positive examples is if this theta parameter is actually very, very large. That's the only way I could see all positive examples with high probability. Right? So it turns out like we actually did learn something. We learned that theta, the ground truth parameter for F star, is actually quite large. Okay, now we're like sort of in good shape, okay? So if we could somehow test, not Gaussianity, but that the marginal distribution of D prime is somehow also concentrated, then maybe we could just accept and say, okay, you should also output positive. Okay, because in the case that D prime is also concentrated, W dot X should also be sort of concentrated. And so theta should dominate. And so we should still just accept and say output all positives. Okay, and in fact, that works. So what you can do is you only see positive examples. You know that theta is large, is at least square root log 1 over epsilon. And you can check that D prime satisfies a type of Gaussian concentration. But the way that you can check this is not by testing Gaussianity per se, but you can estimate the first log 1 over epsilon moments of D prime. So you can actually look at like expectation of, you know, x2, x3, x4, where these come from D prime, just these covariates. So you look at all monomials of degree at most log 1 over epsilon, and you just check that they, you know, we know what they should be for a Gaussian. We know what all the moments should be for a spherical Gaussian. And we just check that all of these moments are actually very close to what they should be if they truly were a Gaussian. And if that's true, then you can prove that you get the concentration that you need from D prime, and you can just accept and say output positive. Sort of makes sense? Yes. You buy it, Sanjay, or no? Okay.
You really need all the monomials. You not just look at the spectral normal.
Oh, good question. So it turns out we have an SQ lower bound that says you need like D to the omega log 1 over epsilon many samples in order to actually TDS learn half spaces, even with respect to Gaussian distributions. So you really do need to look at all of these moments. And I guess I wrote this, or this was in Colt 2024.
Expensive, really, you want to do D to the K. You want to K.
Oh, you have to do D, you have to do D to the log 1 over epsilon. We would love to do poly and D in 1 over epsilon, and I'll talk about that in a second. But this is way better than, okay, my point is this is way better than exponential in D. You never want to pay exponential in D. So I'm going to be happy with D to the log 1 over epsilon, especially since it's the best you can do relative to SQ algorithms. Yeah.
Does this also hold for, like, this is for the whole problem, but the example you showed before was just, you see the specific case of all positive.
Oh yeah, you're right. So there are other cases where you don't see all positive examples.
Right, but for that, this.
No, we have to do something else. You have to do something. Just running a plain old like half space learner, like an averaging algorithm, will work in that case. You can, yeah, and there it's another. I don't have time to explain why, but yeah, that works. This is really kind of the bottleneck. Okay, so, I don't know how interested you are in like, now I've defined the model. We did some toy examples to get you a feel for it. Now, like, if one of these like function classes like really gets you excited, we have results for them. Maybe Sanjay, you were talking about like not a polynomial time algorithm, but it turns out, if your training distribution doesn't have to be even Gaussian, it can be log concave, lambda can be non-zero. If the half space is homogeneous, so like theta is 0 for homogeneous half spaces, then we get like a truly poly D 1 over epsilon time algorithm. And for various other function classes, and scenarios, this is actually an outdated chart. We have improvements on this, but we have a bunch of results of this form. Right. So what I'd like to do is sort of give you a feel for some of the more sophisticated techniques that we have to use to get more advanced results in this model. And they all come down to this sort of transfer lemma, where you're trying to certify that a classifier's performance on D translates to something on D prime. And as I mentioned earlier, like distribution testing will not work. Like I can't test if D prime is Gaussian or not because it takes too many. It's not even like a super well-defined problem. And so one way, like I've hinted at this previously, but one way that you can get around this is to work with something called sandwiching polynomials. Okay, so we say that a function class has sandwiching polynomials. If there are these polynomials PD, P down, and P up that are always pointwise greater than or less than your function, and furthermore, like the expectation of P up minus P down squared is at most epsilon. Okay, so like it sandwiches your function class. And what we can prove is that if your function class, we have this general theorem that says if your function class has an L2 sandwiching polynomial, then it suffices to simply compare and test moments from your base distribution to your test distribution. And you will get a TDS learner for that function class that runs in time D to the order K, where D to the order K will correspond to the number of time and sample, the amount of time, the number of samples you have. And for half spaces, K is about 1 over epsilon squared. So you get D to the 1 over epsilon squared in the fully like agnostic noisy case. And as I said, like the algorithm, as I hinted at earlier, is simply check all of the moments for a particular size that they match, that the moments of D prime actually match the moments of the base distribution. And then if that test passes, run polynomial regression on your training distribution D and output sign of that polynomial as your classifier. Okay. Yeah, so this is there are 4 ideas I wanted to tell you about. I have enough time. I won't be too much longer.
This is not that.
What?
It's one of them.
I know. I'm checking. Yeah, no, I have enough time. There are like 4 ideas I wanted to tell you about. This was the first idea.
So
yeah.
At a high level, then are you saying that this TDS method depends only on some finite number of moments? As long as you test, and that's all that matters. Tails don't matter, and so you're somehow just.
Well, that's idea 1, and idea 1 will lead to a set of results. Okay, now we have other results that will require ideas 2, 3, and 4 that I want to tell you about. So this will only get you so far. Yeah.
Once you test that these moments now, for example, does the training algorithm you run on P matter? Or if the test passes, then you can. any way you want, like find the classifier for D and say that.
No, it's coupled with the type of algorithm that you want to run. In this case, it has to be polynomial regression. Okay. I don't know. Do you want me to prove that this works? Like I'm willing to prove that it works if you want. Should we do this? I can prove you want. Okay, you want me to prove this lemma? All right. Okay. Right. So remember, F star is the ground truth. It has sandwiching polynomials, P up and P down. And what you do is we ran our moment matching test. It accepted, all the moments matched. So then we ran polynomial regression. We found our P, our polynomial, our best fitting polynomial, and we output the sign of that polynomial P. That's our classifier, okay? And what I want to bound is the error of H with respect, the error of my classifier, the sign of a polynomial with respect to the test distribution. That's what I want to bound. That's all we care about. Okay, so I need to bound this probability. Everybody with me so far? Okay, so it's not hard to see that this is at most the expectation of D prime of P of X minus F star of X squared. Okay, this is like easy to prove because H is the sign of P. Okay, now this is at most like 2 times the X. I'm going to use the triangle inequality here. P of X minus P down of X squared plus 2 expectation of P down of X minus F star X squared. Okay, right? Everybody okay with that? Okay. Now notice that, and this is D prime. These are D primes.
Does that squared go inside the expectation?
Oh yeah.
Make sure you're missing a closed parenthesis.
Yeah, sorry. Like it's a little live wire act here. You try this. Okay. I'm wishing a closed paren somewhere. Oh, yeah, sorry. Oh, I did that wrong. Whatever. Okay. Now what we know about F star is that it's upper bounded by the upper polynomial, right? So for this term, I can bound this by expectation of D prime PD of X minus P up of X squared, right? Because the upper polynomial is always an upper bound on F star of X. But this goes to 0 because it matches moments with respect to D. And so this basically gets canceled out, goes to epsilon. Okay, so that term's okay. Now we're left with like this term, right? Okay, so I'm going to use the triangle inequality again. This time I'm going to add and subtract. What do I add? F star, right? Oh, right. Okay, we'll do that. Right. Yeah, I was going to do that. Yeah, so notice that since P of X and PD of X are polynomials, right? P and PD are polynomials. So I can go, remember I had D prime here, this expectation with respect to D prime. I can switch to the expectation with respect to D because they moment matched. We ran our moment matching test, okay? Now I can add and subtract. So now I'm with respect to D. So now I can add and subtract F star of X. Okay, all I did was add and subtract F star of X. But again, this, if you look at this term here, we have the upper polynomial, upper bounds F star of X. And so this will go to epsilon. And then I know that since I did polynomial regression, P is the best fitting polynomial. So in particular, this is less than or equal to the expectation of PD minus F star of X squared. Because P was the best fitting one. So it's doing better than PD. But now I have PD here, and I can replace F star with P up, and I can go to epsilon again. So you can get a feel for like why these tests are important. I can play these triangle inequality games with sandwiching polynomials, and I can switch between the key like subtle maneuver here is I can switch between D and D prime because I know that the moments match. Okay, and so that's why the algorithm works. Very simple. Yeah.
This is an adversarial sort of question.
Okay.
So this whole business then works, gives you a positive result only when D and D prime are super close, in which case I can do packets or whatever other, when D and D prime are far away, everything falls apart anyway, so.
Yeah,
Sort of new operational.
Okay, first of all, no, even if D and D prime are very, very close, I still don't know how to like prove that any previous algorithm works. Like, because basically they could be really close, right? Like distribution, like in TV distance. But then when you take two training samples, because you've sampled repeatedly, the TV distance between your samples, your training, those are quite far. That's large. It's actually like a very, very hard problem. It's
so it's a closeness with respect to this error function class.
Yes. Okay. Sorry, my handwriting. Anyway, let's get to some more. Oh, right, harder results. I'll only spend 5 minutes on harder results. So now let me try and address some of your concerns, Sanjay. Okay. So it turns out for half spaces, you can achieve like poly d 1 over epsilon instead of d to the order 1 over epsilon squared. You can do this, and we don't rely on moment like just on moment matching. We have to use moment matching, but the actual algorithm that we run is we have to run SGD on a non-convex loss due to some results of Diakoniklis et al. And Vasilis to obtain like some candidate hypothesis that's actually close to the ground truth. And then we have to test various distributional properties that we have in our training set, namely anti-concentration and concentration, in order to say something about how close W and W star are. So, sorry?
Why does
I'll tell you in a second. So like the main transfer lemma we get, what we want to prove, maybe I have just a picture to speed up time. Like, and this is the second idea that I wanted to tell you about. So imagine that V1 is like, we run our algorithm and like this SGD on like a non-convex loss, and we get this V1. Like what I want to say is that, if I have another vector V2, like an arbitrary other vector V2, this shaded region is the error region. And what I'd love to be able to verify is that D prime doesn't put too much weight on this error region. If that's true, I'm sort of in good shape. It means that whatever I trained on like is going to perform somewhat well with respect to D prime. In order to test that, I need to know that D prime has both some anti-concentration and concentration properties. It needs to be like relatively spread out, but not have tails, so that I can do these tests. And it turns out you need to look at you need to do a spectral test on so you run your algorithm, your SGD algorithm, you get V1, then you have to look at these projection matrices, and you have to do spectral tests on these projection matrices in order to verify that these regions aren't getting too much weight. That's like, at a high level, that's what happens. It's actually quite technical. But we call this idea localization, because instead of these global moment tests that you're doing about the entire distribution, where you're just looking at moments of the covariates, here you're looking at distributional properties relative to like some fixed classifier. So you're localizing, you're looking at some restriction of the space. Okay, and this builds on some like work that Vasilis has done. It's like one of the key papers for understanding this, but that we call localization, and that led to this notion that we have called localized. Remember, I talked about discrepancy distance in the beginning. It turns out that we can define a notion of localized discrepancy distance, which does admit efficient tests. And we can do chow matching. So instead of just matching the moments, we match the moments multiplied by your classifier. So like Gautam came up with this trick. And that enabled us to get away with to TDS learn function classes that have L1 sandwiching polynomials instead of L2 sandwiching polynomials, which turns out to be a big win. Yeah, so also using these kind of tricks, we can actually get all the results that I talked about where we're getting order lambda for our error, we can actually get it down to just lambda, like 1 times lambda, if you have the appropriate sandwiching polynomial. So the third idea that I want to talk about is, and sort of another question of relaxing, like what if we want our TDS algorithms to accept as long as the TV distance between D and D prime is small, rather than being equal? We call this like a tolerant TDS learning algorithm. And there's this very nice paper in Europe's by Serbi and Abhishek Shetty and Kostas and Arsen, where they showed how to do this. And this is main idea 3. They came up with this very elegant outlier removal algorithm that basically says if you have a polynomial, then they come up with a selector function. Like they have a training set, and they basically say, you know, they figure out how to weed out points such that with the points that you're left, the variance of any polynomial is sort of close to the variance of what it should be with respect to the base distribution. So you can come up with these algorithms that really find points in your training set that would push the value of low degree polynomials to be very, very large. So they have some kind of an iterative process that does this. And that enables them to get these tolerant TDS learning algorithms. Then, you know, I was fascinated by this. And so then we came up with like an L1 version of this outlier removal. And that enabled us to come up with an algorithm for learning AC0 with respect to contamination. This problem had been open just in this ordinary like learning literature for like 30 years. We were able to use these techniques to solve this problem. So that was nice. And then I guess like the fourth idea, which I really don't have time for, is that you can do moment matching, but in a data-dependent way for data-dependent feature maps. So we figured out how to take, this is with Gautam and with Lin and Costas and Arsen. Oh no, Arsen's not. This is the one paper Arsen's not on. Sorry. Where we had these, we showed how to import kernel methods to the TDS framework, and this enabled us to learn one hidden layer neural networks, even if in the presence of distribution shift. So this was just at iClear. We're also able to come up with like end-to-end results where you like say you don't even want to take an assumption on your training set. Well, then you can run a testable learning algorithm on your training set and compose the results with the TDS learning algorithms. In order to do this composition, we have to like use sum of squares proofs to check things about both about the training set. We also have some results on what we call universality. So say you want an algorithm that you have your training set is Gaussian. It turns out we can come up with algorithms that will accept, Sanjay, any test set as long as the fourth moment is bounded and you have an upper bound on its density. So like you can accept like a very large class of distributions in that setting. You do have to assume your training set is Gaussian. We also have results that actually separate train and test time. So if you'd like to train for longer, you can come up with like super efficient tests at test time to figure out if the distribution is shifted or not. We have another Cole paper that can extend this to like not just half spaces, but intersections of half spaces. We prove a bunch of SQ lower bounds. You can prove that you can't do TDS learning for like monotone functions or indicators of convex sets. Yeah, so just some concluding thoughts that I really like TDS learning because as somebody who's worked in computational learning theory for many years, like the techniques there are very limited. You either have sort of Fourier methods or boosting, and here in TDS learning, you really get to make use of a much wider array of tools from TCS and come up with like much more sophisticated algorithms in contrast to like PAC style results. And again, you know, is epsilon delta learning like actually learning, or should we call it like imitation or mimicry? I think that domain adaptation is like a much more meaningful setting. And, you know, taking assumptions that you can't verify often undermines provable results. So I'll just stop here. Thank you. Any question? Yeah.
So this distribution defined using for your transfer lemma to test whatever property you want to test. Is it used after that point at all? For example, when creating your classifier, do you use?
No, good question. We've thought a little bit about like a setting where you get a very small number of labeled samples from D prime, and what can you do with that? And we don't have a that's a very interesting question. We don't have a satisfying answer for that. Yeah.
So maybe asking a similar question. You gave results for when there's like little to no covariate shift, but it seems like all of the results can handle arbitrary posterior drift. Is that true? All like conditional of y given x would just be crazy for p prime versus d.
Well, then lambda will be very large.
Yeah, but it just scales with lambda.
Yeah, lambda takes that into account. Okay, thanks guys.